Hello, hello everybody. Thank you for joining. Making just a small sound test. Can people online hear me well? Or do you just see me moving my lips? Nice, perfect. Well, thank you everybody for joining. Today we'll be talking about the age of truly digital money, and it's a little bit about the current status of cryptocurrencies, what's in the line right now, what's happening, but we'll go a little bit into the history of where it came from and what are the issues that are trying to be solved. So, the goal is for you to gain an intuition about how this works, how Bitcoin currently happens, how blockchain helps it, and you to gain how things fit together. But also with this, for you to protect yourself. Once you know how it works, then you can also see beforehand if there is something fishy or doesn't look like it is correct. Through our agenda, it's a little bit of a big agenda, but we will go through a thought experiment first, so to see which are the problems that started this and went to getting into digital money. Some cryptographic technicalities, so we will go through them. It won't be anything that complicated, though. If you have questions, go to the cryptography video or, well, ask us later. Also, we'll go through blockchain, Bitcoin, some alternative coins, and a tiny little bit of Ethereum. So, without further ado, we can start. So, let's start with a little bit of a thought experiment. We'll talk about the Byzantine generals problem and how this goes. We have several Byzantine generals who want to attack a single place, and in this case is the castle in the center. They all have to attack, or at least some part of them have to attack at the same time in order to conquer the castle. If less than that amount attacks, they lose. So they can communicate between them, they can send messages within them. They need, in this case, at least 3 to attack in order to win, and they have to reach consensus, so they must do whatever the majority says. So if 3 say attack, they all attack. If 3 say retreat, they all retreat. So this is the basic idea. So let's imagine this scenario. 2 generals say we attack. 2 generals say we retreat. So it's up to the tiebreaker, the last general, to say what's the action. But let's imagine this general is a traitor. And he sends the message to the 2 who say attack, yeah, I'm going to attack. And to the 2 who say retreat, yeah, I'm going to retreat. So what happens? The 2 that say attack, they say, well, everybody's going to attack. They do it, they lose. The others say, well, we're going to retreat. They go away. And that's the problem of consensus that comes from this thought experiment. How do we get all the loyal generals to reach consensus, to agree on a strategy despite the traitors, despite the people who lie? And this is connected also to the problems of digital money. How do we reach consensus about how much value everybody holds? So let's think a little bit, taking a step back, about the problem of digital money. The first one, how do we translate money from a physical space, which we are accustomed to, into a digital space? So let's take a naive approach. Let's say we have a 50-euro bill. Well, every bill has a unique ID. And we say, well, let's replicate that. Let's make a coin with those unique IDs. So easy. How do you pay? In order to pay, I say, well, I have coins number 4, number 5, and number 6. To pay, I say, well, here, take coin number 5. I share you the ID. And then I don't use it again, right? Well, it doesn't work that way, and we'll see also. But let's suppose this is fixed. There's a way to translate it into the digital world. We have the next problem, which is the agreement problem, how much everybody holds. We have two persons, Alice and Bob. Bob wants to send 15 of these digital coins to Alice. So he says, well, I send you 15 coins, don't worry, I hold 20, so I should have enough. Okay, Alice says, all right. But then comes a third person, Charlie, who says, wait a minute. Bob told me that he only holds 10 coins. So who does Alice believe? Who of these is lying? And the Byzantine general problem tells us that this problem in particular is not solvable. You need at least 3 + 1 loyal or truthful persons per each liar in order to reach consensus. Let's imagine we solve this problem. Then the double spending problem. Here is Bob. Bob has 20 coins. And both Alice and Charlie, they agree on that. They say, well, Bob has 20, we agree on that. So Bob says, well, I'll send you 15 coins. Perfect. But at the same time, Charlie, he sends 15 coins to Charlie at the same time. So he spends the money twice. And until later, Alice and Charlie say, hey, Bob sent me 15. Oh. So these are some of the problems that come from digital money. These are the most important ones, but we have others. For example, we need a network of people who is communicating that agree on a certain value. So let's imagine we came across all these problems. The problem of making money digital, we solved it. We have the problem of consensus, we solved it. We have the problem of double spending, we solved it. Now we have a network of people who can communicate and have to come and agree together. We have a message that goes from one part of the network up to the other side of the network. We will call this the latency problem. How long does it take for a transaction to go from one place to another, for a certain consensus reached from one side of the network to the other? The second problem, well, all of this, well, the next problem, not the second, all these people are communicating. What happens if, for some reason, a group of these people is separated from the rest? So this group on the left, they are agreeing on something, and the group on the right, they agree on something else. And once that disruption is solved, how do they reach consensus? Again, this is the network disruption problem. We also have, well, still traders and liars. And inflation, how do we create money in here so it doesn't lose value or it doesn't become overvalued? So there are many problems. This is for digital cash. And there have been several attempts, so we'll see a little bit about these attempts. But let's just sidetrack a little bit to talk about credit cards. What's the deal with credit cards? It's the closest thing we have to digital currency. It's quite easy to use. You go to the store, you don't have to pay, you reach to your credit card and you pay. Done. But what does this payment mean? Means that you first trust your bank. Second, you trust your card network, whoever that is. And third, you trust a little bit in the store. New technologies help us so stores cannot steal our details, but still you need to trust it a little bit. But there is also the problem that the store has to trust the card network and the store has to trust its own bank. And this is just the basics. There are more chains of trust. So, and privacy? Whoever tells you that nobody of this keeps your data says, oh, that person went to buy this and that place at this time with this amount. What's the deal with cash? You and the store agree on a single token, and that's all. You don't need to trust the store. You don't need to trust anyone else. You just need to trust the token. And you can go to the store. Here's a 50 euro bill, and the store person will say like, yes, it's a perfectly valid 50 euro bill. Perfect. We can do business together. And I don't even need to know your name. So that's the deal with cash, and that's what we would like to replicate in a digital manner. Some of the first attempts, DigiCash. These are not the only attempts, but some that moved it forward. DigiCash, they introduced a thing called cyberbucks. And they said, well, cash is about about anonymous transactions. So they said, well, let's use this fancy thing called blind signature technology. And with this, they included a way of paying to other people without anybody knowing who the other person is. And some merchants and banks accepted it. But it didn't work, and it filed for bankruptcy in 1998. Well, next attempt, e-gold, money backed by real value. They said, well, can we make a token that is backed by gold and you can exchange it the same way that we exchange gold? So we all agree on gold, or should. They allowed micropayments up to 1/10,000 of a gram of gold you could pay to another person. It was centralized but somehow anonymous. So they allowed for you to say, I'm going to give this amount of grams or parts of a gram to another person without that person knowing who am I. Though it was shut down by the US government in 2008. This was because it was used for a lot of nefarious purposes, to put it in a way. Money laundering, commission exchange, corruption, and a lot of things. So this was why they shut it down. And because it was centralized, the US government had power in order to shut it down. Then we have Hashcash. Hashcash was an idea in order to replace postage in mail and solve the double spending problem with cryptography. Now, they introduced the idea of proof of work, and we're going to go into a little bit more of detail of what this proof of work is, but to give you an example, when you send regular mail, you have to pay a stamp for it. That's the proof of payment. You want to send a single letter to somebody, you pay for a stamp, and you send it. Easy peasy. If you want to send 100 letters, you pay for 100 stamps. So if you want to send the spam, it is expensive. You have to pay something for it. What happens with email? There's not much difference between sending 10 emails or 100 emails. It's almost the same expenditure for you. So in order to avoid spam, this person introduced, how about you proved that you expended certain computational resources by solving a mathematical problem. If you can solve that problem, you can send one email. You solve again, or a kind of a little bit different problem, you can send another email. That's the gist of proof of work. Then B-Money. B-Money introduced the idea to create money within the system. So it was outside governmental systems and it was decentralized. I would have liked to get a logo of this one, but didn't find. This was more like an academic introduction of the things. And, well, it was nice, but it didn't got track. Then we get to Bitcoin in 2008. It solved all of these problems. It took together what these types of payment brought to the table and said, well, we'll have secure digital transactions. We're going to use cryptography to secure exchange. We're going to allow for micropayments. We're going to create money outside of government regulation and use proof of work to validate information. Now, a funny thing about Bitcoin, it started with this paper, Bitcoin, a peer-to-peer electronic cash system, written by Satoshi Nakamoto. And in this paper, he introduced how it should work, what the technicalities behind it. He introduced the term of blockchain, who put it as the backbone of Bitcoin, and pushed the community forward. At the beginning, Satoshi Nakamoto was the one who convinced the community to start mining Bitcoin and how to work through it. Some years later, Satoshi Nakamoto disappeared. And the thing is that Satoshi Nakamoto was a pseudonym of a real person, so nobody knows who exactly this Satoshi Nakamoto is. So all Bitcoin started with this mystery. Nobody knows who Satoshi Nakamoto was or is. There are some ideas, but nobody has confirmed it. And Interesting about this is that Satoshi Nakamoto holds a fortune in Bitcoin because he was the first of the miners. So whoever that person is rich. Well, now to understand Bitcoin and to understand how it works, we'll go through some technical basics. Now, up until now, any questions? No. You can write them, check in the live chat, so let me know at any time if you have questions, and hopefully I'll see them. Well, the technical basics. The first one, hash functions. We've talked a little bit about this, but what is essentially? So we'll talk about it. A deterministic one-way function. Let's put it this way. You get an input, say some fruit in this analogy. A hash function will be something that will get this input and get some output, like in this case, well, some juice. The idea from this is that it should be really easy going from left to right. So from the input to the output should be fairly easy. You get the fruit, you get an output, but you also should get the same output. If you input fruit, you shouldn't get a shoe, you should get juice. And the opposite should be really hard or close to impossible. So if you start with juice, you shouldn't be able to get the fruits back. And this should be a super blender. It means that it should be able to get anything. You should be able to put images, any type of information, anything you can think of, you should be able to put it in this hash function, and it will always return a value. Now, how is it useful? A hash function should always return a unique output per input. Whenever you put the same thing, you should get the same thing out. But also, there should be any small variation in the input should create a noticeable change in the output. So in this example, we have this is a text. We're going to use a hash function called MD5. The name is not important, but it's a hash function, and we get the value on the right. Let's change it just a little bit. How about this is a test? I should get a completely different value. And this should be noticeable or large. So one bit changes, completely different hash. So this can help us as an integrity checker. Let's imagine you want to download a big file from the internet. Let's imagine like Ubuntu desktop. This is a large file, it's 2.6 gigabytes that have to come from a remote server in somewhere, pinpoint through a lot of systems until it reaches your computer. That's more than 2 billion bytes traveling through the internet, and you're relying that every single one of them will be exactly a cent. But if a single bit changes, you have a different file. So what they will do, they will give you the hash of that big file. So therefore, they will give you, well, this is the file that we have, this is the hash of that file. So when you download it, you can calculate the hash of your file, and if the hashes are the same, you know that you have identical files. So if one or more of the 2.8 billion bytes in this file is different, you should get a different hash, and because of that, notice that you have a different file. So that's about hashes as an integrity checker. But hashes can also help us work as a proof of work. That's another function that hashes were used for. And we exploit for this the unpredictability of hashes. This means that whenever you have something that you put in the hash function, you shouldn't be able to say something, anything about the output until you calculate it. So let's imagine this scenario. Somebody says, I'll give you an ice cream if you can give me the hash of a number that starts with a 0. Easy as that. I'll give you the ice cream if you can get the hash of a number that starts with a 0. And this is the hash that starts with that. So you say, well, let's start with 0. I get this hash. Starts with a 0? No. How about this next number? Doesn't start with a 0. The next number doesn't. Next number, and so on, until I reach a number whose hash starts with a 0. I go with this, and I get an ice cream. What this proves is that because there is certain probability for that condition to happen, I have to search for that hash until I get that particular characteristic. And that proves that I expended computational resources in order to find it. That's a proof of work. Now, we've talked about hashes. Let's change a little bit of subject and we'll talk a little bit about cryptography. How normally happens. Let's say Alice wants to send a message to her grandmother, Bertha. What does she do? What does she do? She gets a message, love you, Granny. And she has to send it securely to her grandmother. So she will take an encryption algorithm with a key. As an analogy, she will take a box, she will put the message in there, she will grab a key and lock it. So as long as and she can send the box. As long as nobody has the key, the box cannot be opened. So we have something unbroken, or that cannot be broken. In this case, a ciphertext. In our analogy, a closed box or a locked box. Bertha, in order to read that message, she would have to use a decryption algorithm with the same key. In our analogy, she would have to get a copy of the key that Alice used to open the box, and she can read the message. So, easy as pie. But we're not interested in this type of cryptography called symmetric cryptography. We want to use a newer one called public key cryptography. In the previous case, we used a single key. The same key that locks is the one you use to unlock. But in this case, we're going to use two keys. We'll call it green and red. Whenever you lock something with the green key, it can only be unlocked with the red key, and the other way around. If you lock with the red key, you can only unlock it with the green key. By convention, one of these keys will call it the public key, and the other key will call it the private key. So what do? You save your private key, and you give a copy of your public key to everybody. So everybody should have a copy of your public key. So if somebody wants to send you a secure message, they will lock that box with your public key. So only you should be able to open it. Only you should be able to read it if somebody encrypts it with your public key. But what happens if we do the contrary? What happens if I lock the box using my private key? Everybody can open it. Yeah, but why is that useful? Well, that's the basics of a digital signature. If somebody can open a box that I close with my private key using the public key, it means that I am the owner of that key. That means if somebody can decipher a message with my public key, it means that only I could have sent it because only I should have a copy of the private key. And that's the basics of public key cryptography and how a digital signature works. This is not exactly how it works. You garble it a little bit more, but it's the basics. So we touch about these subjects. Hash functions first. Now public key cryptography. Now a third topic. The blockchain. The blockchain is basically, a chain of blocks. And how does it work? Each block contains information, some data, time, what time it was created, and this is the key part, a hash of the previous block, and a nonce, which we'll go through it later, but we'll call it a nonce. And this is the key part because it means, for example, block 11 contains a hash of block 10. Block 10 contains a hash of block 9, and so on, until you get to block 0, which we'll call it Genesis block because it doesn't have a previous one. So for example, let's say you have a ton of blocks. You have until block 101. And you want to change block 11. If you change block 11, the hash changes. block 12 has the hash of block 11. Yes? So if you change block 11, you have to change block 12. And now that you change block 12, it generates a different hash. So you now have to change block 13. And the next block, and the next block up until the one you have. So this is how a blockchain works. You have a reference to the previous one using a hash function. Whenever a previous block changes, you have to change all the ones that are next to it. And we'll see later how this achieves immutable past. And now we're ready for Bitcoin. With these three things, hash functions, public key cryptography, and blockchain, we can build a digital money. Any questions? No? All right. Now, Bitcoin is basically a shared blockchain with transaction information. You remember, the blockchain, each block contains some data. In the case of Bitcoin, it contains transactions. That's basically it. And everybody agrees on the same copy of the blockchain. How do they reach this? First, some of the components. First, everybody has an address. That address is composed of two parts, a public ID and a private key. The public ID is useful when somebody wants to send me money. It's my address in this sense, and whenever somebody wants to send me money, they have to use my public ID. And you can create as many addresses as you want. They are for free, and you can create a ton of them. Then, second, the blocks contain transaction information. So it says who paid who and how much. But in order to send a transaction, that transaction has to be signed by the person who sends it using their private key. This is where we attach public key cryptography. What are the rules of Bitcoin? Rule 1, anybody can add a block. That's the basis of it. If you can create a valid block, and I'll say why valid is in bold, then everyone will accept it. That's the rule. You see a valid block, you accept it. So a block has all this information, has data, time, hash of previous block, and a nonce. Now, in order for a block to be valid, you have to make a proof of work out of it, and you have to generate a hash with a certain amount of leading zeros. So you say, well, I have my block, it has all the information from the transactions, and I will generate the hash of it. Does it have, let's say, 10 leading zeros? No. So I change the nonce. Nonce come from number used once. So you add 1 to the nonce. You change it. Calculate the hash. Does it have 10 leading zeros? No. You change the nonce. Does it have 10 leading zeros? No. So you start changing that number until you get a hash with that characteristics. And that is mining a block. So it's basically a lottery system because if everybody is mining, everybody have as much the same probability of getting a valid block. So in some moment, this person will get a valid block. On the next moment, this person will get it, and so on. So this is the idea. You get as much chances of getting a valid block as your computational resources. And that's the idea of this lottery system. Now, rule number 2. Everybody works in the longest chain. So if there's a chain longer than the one that I have, I drop mine and I accept the longest one. How does that work? Let's imagine we have this chain. So 2 people at the same time discover a valid block. So some people start working on top of the purple chain. Some people start working on top of the black chain. And they continue. Sometime later, a person discovers a block here. So everybody drops the purple chain and start working on the black area, on the longest chain. And this can happen several times. And whenever this happens, the area that is dropped is lost. Everybody say this is wasted work, and they continue working on the longest chain. So rule 1, whenever there's a valid block, you accept it. Rule 2, you work on the longest chain. Rule number 3, every block creates money. So each time a new block is created, some Bitcoins are created with it. At the beginning, it was 50 Bitcoin. Whenever you achieved a valid block, you would get 50 Bitcoin for it. And this goes to the person who found it, who we will call the miner. So the miner gets those 50 Bitcoins. And this number halves every 210,000 blocks. This means that for today, you only get 6.25 Bitcoins per block. That's the idea. Other rules, more basic than those. A new block should be created every 10 minutes, more or less. A proof of work complexity is recalculated every 14 days because if more people join the blockchain as miners, it will be easier to find new blocks. So this time goes down and maybe new blocks start getting every 6 minutes or every 7 minutes. If less people are in the blockchain, well, this time goes up. So the complexity is revised every 14 days. A transaction is confirmed once it has 6 blocks after it. So your transaction goes into one block, is not written in stone until it has at least 6 blocks after it. If a block is created every 10 minutes, it means that it requires 1 hour for your transaction to be confirmed. And the block reward is halved every 210,000 blocks. Now the incentives. The miners are wasting or they are using resources in order to confirm transactions and to say, well, this person paid to this other person, this happened inside the blockchain. So there should be some incentive in the way of money to say, well, keep working it. So the first incentive is mining a block. Each block confirms transactions. And if you discover a block, you get a reward. In this case, well, 50 Bitcoins at the beginning, now 6.25. But there's also a miner fee, which equals to the transaction time. Now, how does this work? Let's imagine this. There are two persons who one wants to pay a Bitcoin to the other. So she wants to send 1 Bitcoin to him. So she puts inside the transaction 1.1 Bitcoins. Of course, the fees are much lower, but let's go with 1.1. She puts 1.1 and he receives 1 Bitcoin. The 0.1 that remains goes to the miner. So this becomes a marketplace. The higher you put in your fee, the more it's more likely that a miner will take your transaction because the miners are the ones who decide whose transactions are in the next block. So if you put a higher fee, a miner will say, oh, this transaction, I should put it in the next block. That's the main idea. Those are the two incentives. Because as you can see, the incentives of mining a block will continue decreasing until it reaches 0. This will happen in year 2140, where every block will create 0 Bitcoins and there will be a maximum of 21 million Bitcoins in circulation. So all the incentives will go to the miner fee. So every transaction has a cost. Now, how all this works together in order for you so you cannot cheat at Bitcoin, so you cannot rewrite the past. So let's say everybody is working at block 91, but somebody wants to change the past. Let's imagine a person said, well, I paid 1,000 Bitcoin, but I want to retract it. He could rewrite that block and then create the longest chain, so everybody would accept it with the new block. But in order to do that, let's imagine it's block 74, that person should create 18 blocks of expensive computing before the next block is added. This means that before people in block 91, at least one person wins the lottery, this person has to win the lottery 18 times. Is this possible? Well, yes, it is possible, but you should control at least 51% of the computational resources of the whole network worldwide. If you control more than 51% of the computational resources worldwide, it means that you can change the past. But this brings us a step forward from the Byzantine problem with which we started. The Byzantine general's problem says you need at least 3 loyals for each liar. Here, you need that at least half of the people is loyal. So, 1 loyal per each liar. Now, Bitcoin value. You've all heard about Bitcoin value, but where it all started. And it started in 2010. It was a funny story because everybody had a lot of Bitcoin and said like, oh, I don't know if this is useful. I mean, I have a lot. So this guy, Laszlo Haynes, said in a forum, I'll pay 10,000 Bitcoin to whoever sends me 2 pizzas. And you know, it happened. Somebody accepted those 10,000 Bitcoins and sent him 2 pizzas. So it was the first time a Bitcoin represented value, up to less than a cent, but it represented value. And this date is celebrated in the Bitcoin community. Bitcoin value today started near to 0, and in 2018 it reached up to $20,000 per Bitcoin. So with 5 Bitcoin you would have get $100,000. Right now it oscillates a lot between, I don't know, $6,000 to $10,000 per Bitcoin. So let's mine some Bitcoin. It looks like it's really good. You get 1 block, you get 6 Bitcoins. But you're not the first to think about this. Some people said like, well, in the beginning it started with CPU mining. People would say like, well, I'll use my computer to mine Bitcoin. And it worked. But then other people said, well, I have this graphic card that I use to play my games. Maybe I could use it in order to mine Bitcoin. And it started the GPU mining era, the graphic processing unit mining. And it got them an edge. If you had a GPU, you would mine faster than a person who had a CPU. So everybody started to shift to GPUs. Then people said, how about we make hardware specialized for mining Bitcoin? And started the ASIC mining era, where specialized hardware just for mining Bitcoin was created and got them an edge over GPU. But then people said, you know, it's a waste of resources if everybody's trying to win Bitcoin. I mean, it was funny when it was just 100 of us, but now that is 1 million, it's not funny anymore. How about we make a group? We should all mine the same block, and whoever wins it, well, we share the spoils. And this is a little bit like a lot of people buying the lottery ticket and saying, well, if anybody wins it, we share it. And I'm guessing some of the developer projects will find it like, yes. Now, how does it look? Well, close to now. This is 2017. And the infographic is really good, and the blog closed, but still 2017 is not that long ago. We'll use some terms. Gigahash means 1 billion hashes per second. 1 terahash, 1 trillion hashes per second. 1 petahash, 1 quadrillion hashes per second, using small billions or American billions. So if you use a non-specialized hardware like your GPU, your CPU, you would get up to 3 gigahashes. This means that for 2017 standards, it would take 500 centuries in order for you to mine a block. You have a chance of 1 in 2.7 billion. How about the ASIC hardware? Specialized hardware, you can get up to 13.5 terahashes. This means you get a chance 1 in 600,000, or around 11 years. Once every 11 years, you should get 1 block. And the biggest groups by then, they could get up to 1,000 petahashes. They would get a block every 50 minutes. That was in 2017. Bitcoin has all this, solves a lot of problems, but also has some shortcomings. It's way far from perfect, but it works. Some of the first shortcomings is the number of transactions. Bitcoin averages around 4 to 7 transactions per second. You may say, well, ain't that bad, though this is worldwide. Visa gets up to 65,000 transactions per second. Problem number one. Problem number two, the confirmations. We've talked about it. Well, if a block is added every 10 minutes and you have to wait until your transaction is in a block because a miner chooses your transaction to put in the next block, then you wait up to 6 blocks to confirm it. Then means you wait an hour after it has been added to a block. In the best cases scenario, because you have to remember that your transaction is competing with all the transactions and with all the fees. So if you have the highest fees, your transaction goes into the next block and there it goes. And the third is an environmental problem. This comes from a study called the carbon footprint of Bitcoin. And they calculated about how much resources were expended as proof of work, which is wasted resources. And they come up with a number that Bitcoin mining amounts for 23 megatons of CO2 every year, which is about the carbon emissions of Jordan and Sri Lanka, just for mining Bitcoin for a proof of work, which is a waste of resources. So these are some of the problems of Bitcoin, but we are going to say, well, Bitcoin, well, it works, has some shortcomings, but why did it get so much value? Why did it get up to $20,000 when it started with less than a cent? And we'll touch another technology called Tor. Tor is a protocol, is a community for anonymizing traffic. And the idea is this: you want to anonymize your traffic, you put it inside the Tor network will get your message, will bounce it through a lot of systems until it reaches the destination. So for the destination, it should be really, really, really hard to know who sent it. That's about anonymization. Bitcoin is not anonymous, but it's close. We'll call it pseudonymous. And it's about all the information is public. You know who paid who. Everybody is identified by their public ID. And in the blockchain, you can check all the transaction that has happened to every single ID. But you don't know who is each ID. But once you can match from the ID to the who, you know all the history of that person, every single transaction of that person. So if you can protect that part, you have an almost anonymous coin. So what happens if you mix these two? You mix an anonymous network with an almost anonymous payment device. You get the ideal market. For a black market, you get the ideal scenario for exchanging illegal goods, for exchanging weapons, exchanging drugs, exchanging pornography. And this was not the first, not the last, but maybe the most famous was the Silk Road. And it relied on Tor network in order to have everybody put what they want to sell, what they want to buy, and Bitcoin to exchange value. Of course, it was close, but this just got the thing started. And there are other bad uses for Bitcoin. It has been used for money laundering, for Ponzi schemes, for ransomware payments, and many, 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 many more. So some people say, well, yeah, Bitcoin, yeah, it's okay, but I think I can do it better. So we came to the subject of altcoins or alternative coins. So up until now, questions? All right. Altcoins or alternative coins came from a different idea. They say, well, Bitcoin solves a problem, but not all of the problems. So let's get it straight. First, remember that time when one Bitcoin was less than a cent? I mean, if you would have had $1, you could buy a ton of Bitcoin at that time, and then you would be rich right now. Some people said, I would like to go back to that time, go back to that era where it was really cheap. They created a new coin and said, well, Xcoin, it's a new big thing. You should buy Xcoin. But these people were sneaky because they pre-mined the coin. Before making it publicly available, they pre-mined 600,000 coins. So they would say, well, if this thing ever gets value, we already have 500,000 coins. This was the first, not the last. Other people say, well, Bitcoins helps for money. It's really good. But how about we use it for something else? I mean, we have unique tokens that can represent some value. And they said, how about we use it as a decentralized naming system? Something like DNS, where every coin represents a name in the internet. And you can resell that name. The name is yours if you mine it first. And you can resell it as you would resell any coin. It was a good idea. Other people said, well, Bitcoin's proof of work is kind of a waste of time. How about we make it useful? Let's make a useful proof of work. They come up with Primecoin. They said, well, how about the proof of work is to find large prime numbers which has scientific value. So every time you want to mine a new block, you find a large enough prime number and you get a block. That was Primecoin. How about faster blocks? Well, Bitcoin had one block every 10 minutes. Let's make it faster. And they created Litecoin, a lighter version of Bitcoin with faster transaction time. And they inspired themselves in silver. If Bitcoin was gold, they were silver. And just for the lols, I really like what it says. Wow, much coin, how money, so crypto, please mine. Some guy said, well, all these cryptocurrency things, well, it looks like a big joke and I'm going to prove it. So he created a coin called Dogecoin, just for the fun of it. And it actually caught up and has a community with it, though it doesn't have a maximum number of coins, so the value is always low. And it started with this tweet. And a lot more. There are a lot of altcoins. I mean, you can create your own altcoin. You just have to clone the Bitcoin repository in there. You just name it differently and you have an altcoin. But there is one that kind of made the difference. Ethereum. Ethereum was also an alternative coin. And they say, let's boil the ocean. Everybody creates a new coin. We have a new community mining a new set of blockchain. You will create another coin. It's another community with a new blockchain and everything. Let's create a single currency to rule them all. So it would be a generalizable coin, a single group of people working on the same blockchain for new coins if you want, for new type of tokens, for new type of things. So they say, well, let's go further. How about a world computer? If all these people are working on the same blockchain, it means it's a big computer. How about we could run programs on it? They created a platform for decentralized applications where the blocks not only contain a coin, they also contain code for running programs. And they created Ethereum, where you have to expend Ethereum. Well, it's another currency inside Ethereum called gas in order to execute code inside Ethereum. So Ethereum, in this sense, is a global open source platform for decentralized applications. And it kind of works. You can see a big marketplace of applications. And all of these are applications that run on top of a blockchain that it's worldwide connected. And it's decentralized in the sense that it doesn't matter who runs it as long as the code is run. And you can have games, you can have social networks, you can have decentralized governments, you can have a lot of values or a lot of things created on top of this Ethereum as an application. Actually, there was an interesting example of some people who said, how about we predict the future? How do you say something about the future? Well, you get experts and you say, well, Mr. Mrs. Expert, tell me what's going to happen from this. And they say, well, I think this, I think that, I think, let's say a yes or no question, we think yes. How about we ask the people? If you ask a big community about the outcome of an event, you will have people who know a lot, you will have people who know little, you will have people that guess. But in general, you should have a good sense of what's going to happen. Who's going to win tomorrow's game? Is in 2 weeks, who's going to be the next president? So they made an application on top of Ethereum who would say, well, ask a question and we'll ask it to the community. The community would put Ethereum coin on this question saying, well, yes or no. And whoever gets the answer right will get money back. So it's kind of a gamble on the future. Ask the expert, and the experts, all the people can say, well, I vote on yes, and if the outcome is yes, I get more money. And this is how is the lookout for digital currency right now. We went from the problem of the Byzantine general of how to reach consensus to why we want digital cash, some of the ideas of how to work through digital cash, to Bitcoin, to the alternative coins, and now to Ethereum, who brings it forward. So, without further ado, questions. I'm also checking the chat if you want to ask anything. If not, I'll give a couple of minutes. Well, I'll take that as a no. Thank you, everybody, for joining. I hope you liked this presentation. This is part of our effort within Worth to have a monthly conversation of something related to security, of our Happy to Be Secure initiative. If you have any questions, contact us via Slack, via Confluence, or you can check our Confluence page. You can contact us there. Or you can write us via email. Here's some of the books I used to work this presentation. If you want to know more about this, I especially recommend Mastering Blockchain by O'Reilly Media. This is not yet published. I got a preprint, but it was really good. It explained really good all the things about blockchain, altcoins, and Ethereum. So if you want to know more, you can use it. And well, I have a question here. If people stop mining, does that mean new transactions can be recorded? Yes. In fact, that's that's why there is a need to keep the community alive. If you have miners, you can continue the transactions, and with the incentives, you get miners to continue. But once there is no miner, the blockchain dies. And that's why Ethereum actually was created, because a lot of coins, this happened, that they would have to kickstart a new community and get a lot of people to work on it, and then maybe it would die, so everybody wasted their time. So, do you own your coins yourself? No, actually, I recently got into cryptocurrencies. When I started to research this, I had a university student budget, so it wasn't a big budget. So I preferred to get lunch instead of investing on Bitcoin. Now it's a bad idea. I mean, I saw Bitcoin being valued at $10, but it was like 3 lunch back in Guatemala. So. But I know of a guy who made money here at Worth. So you can ask him. And, well, thank you, everybody.